like 15 minutes into it, are the slides available? And they're posted someplace. I believe it's not difficult to find them. It's probably edu.ietf.org, and there's probably a list of tutorials and by year, and yeah. I should start. Okay, well, welcome everybody to the security tutorial. My name is Rabia Krolman. So why do a security tutorial? Well, security is important in everything, not just protocols in the security area. Also, these days, IETF specs are mandated to have a security consideration section. This is sort of interesting. Why is there not also a, managing? Well, I guess there are. Yeah, because there's a security consideration section which people find extremely intimidating. After they do their spec and design their thing, it's like, oh, what do we put into this thing? There's no sort of magic that you kind of design your protocol and then you sprinkle some dust on it and say, now it's secure. You sort of have to think about security all along while you're designing it. And this is sort of a quick introduction into a potentially intimidating area. It's not actually, it shouldn't be intimidating. It's not like, some other species can do this stuff. And ordinary mortals couldn't possibly understand it. It's like most of the areas, people invent their own jargon, and it just becomes very hard to get started in an area. And I would like actually if all of the areas would do this kind of thing, of making it so that all you have to do is invest an hour and a half of your life and sit through something rather than having to read all these books or these specs that are just so full of acronyms and whatever. So yeah, a plea for cross-fertilization. I think that it's really great to learn things that are not in your immediate area, and it's really great to get advice from people, to have people look at it with fresh eyes. And the best way, and in particular, it's often the case that somebody says, oh, we need a security expert to go help this other group out. And you get these, hundreds of pages of incomprehensible specs. It's, so much better, I think, if you take the time periodically to figure out how to just simply say what your protocol is about, what your area is about. And if you actually want to get advice from something like a security person, it's worth your while to make it easy for them, rather than expecting them not only to be volunteering work to help you, but to have to figure out all of this stuff. Also, no matter how deeply you are in something, I believe it's never a waste of time to take a deep breath and summarize, why is it that we did this? What is, just rethink everything. And the more times you do that, sometimes it actually gives you great insight into, gee, we probably shouldn't have done that. So this tutorial, it's an overview of basic security stuff, demystifying things like cryptography. I'll also talk about some sort of interesting, what I call off the beaten track kinds of security things. There's the usual things that everybody thinks about, which is like authentication, how do you prove who you are at a distance, encryption, but there's a bunch of other things that you wouldn't necessarily think of, and so I'll talk about that. So I'll talk about First thing is introduction to security. What is it? And often, because I'm a security person, people say, okay, we're designing this whatever. You go make it secure. And it's like, what are you talking about? What do you mean by secure? So when somebody says make this thing secure, where you should start is, what problem are you trying to solve? Are you trying to make it so that other people can't read your data or they can't modify your data? I mean, what exactly are you trying to do? And what is the threat model? What can attackers do? And what pieces of it can you trust, that won't get infected with malware? So the internet evolved in a world without predators. So a lot of the protocols just kind of assume that everybody involved wants the thing to work. And so the early papers on security talked about, you have to worry about unauthorized access to data, unauthorized theft of services, and they even talked about denial of service, saying, we don't have to worry about denial of service because it would be illogical for anyone to bother doing that because you don't actually gain anything from it. You'd just be going to a lot of work just to kind of vandalize things for everybody else, but nobody would bother doing that. And of course, we've discovered that's not the case. That's probably one of the worst areas in terms of security. And it only takes a tiny percentage of participants to do an awful lot of damage. You also have to be able to connect mutually distrustful organizations together and share the same infrastructure. And society is getting to depend on the internet not just for being able to do part of society depends on it being reliable. So if somebody can do a denial of service attack and take down the internet, that's really a serious thing, not just worrying about somebody reading your data. So security means different things to different people. So you might want to make sure that your data can only be read by the intended set of people, and nobody else should be able to do that. Or you may think security means that you ought to be able to monitor all communication going on so that you can catch terrorists. And these two are sort of an interesting case because they're mutually exclusive. You want to make sure that some benevolent government can read everything to keep you safe, or do you want to be able to send something that you're sure that only the intended recipient can read it? You may want to make sure that data can't be corrupted, or you might think that the most important security problem, and there's a lot of people who believe the most important security problem is making sure that nobody can access your content without paying for it. Including maybe you should be able to detect unauthorized use of your stuff and be able to destroy any computer that has pirated content on it. You may think that security is that you should be able to track down who the bad guys are, or it might mean that you want to be able to communicate anonymously. And again, you can't do both of those. So what can the bad guys do? They can eavesdrop, perhaps, including they might be able to install malicious software on routers. And so even though you can't wiretap the wires, they now have installed malicious code on the switches and be able to capture and store the data or send it off someplace else. They can send arbitrary messages. A lot of times people think that all you have to do is look at the source address in the IP header and you know who it came from, because maybe you need root privileges in order to transmit something. But assume that things on the internet are just boxes that you can completely program so they can emit any bit stream that they want, and so you can't just believe something based on the IP header. They can replay recorded messages. So for instance, if an ATM machine, if you could send a certain number of bits into it and money would appear, even if you can't, you couldn't have generated that yourself, and you can't decrypt what it's saying, if it has the right effect, that when you replay the same bits, money pops out of the drawer, it doesn't matter that you couldn't actually decrypt what it was saying. You could write malicious code and trick people into running it. And it used to be that people would say, oh, well, don't, boot off on a potentially infected floppy. These days, it's like, don't do anything, you'd have to say, because there's so many different vectors in which you can get malicious code. Exploit all sorts of bugs in software to take over machines and use them in order to attack other machines. So some basic terms. Authentication says, who are you? It's a way of proving across the network who you are. So all you can do is send messages. It isn't like they're going to recognize you from what you look like. Authorization is, what are you allowed to do? So fine, I've proven I'm Radia, but am I allowed to read that file? So that would be authorization. DOS stands for denial of service. Integrity protection is like a checksum on data, and when you transmit things, you have CRTs and stuff to make sure that the data hasn't been modified. But if you're malicious, you could modify the data and put on your own CRT. A cryptographic integrity check is one that in order to create the checksum, you have to know a secret. And so therefore, you can't modify a message unless you know the secret. And I'll be talking about that more. And people should feel free to ask questions, especially if I'm using terms without defining them first. So some examples, again, to motivate what we mean by security. Suppose you want to share a file between users. So the obvious thing would be that you would store it on some other machine, a file store. But then in order to talk to the file store, you have to authenticate. It has to know who you are. And it also has to know for each file who's allowed to access it, so for the authorization. You also have to encrypt the communication to and from the file store, or else an eavesdropper will be able to see your file while you're storing it onto the file store. Something more subtle is that users have to know that they're talking to the right file store, or else some bad guy can say, hi, I'm the file store, feel free to send me your secret data. And users may want to know who posted the data on the file store. Electronic mail. Everybody kind of assumes intuitively what that means for security is that you want to encrypt messages. But you also want to make sure that you know who sent the message. You also might, non-repudiation is sort of a fancy word. It means that when you receive the message, not only do you know it came from Alice, but you can prove to somebody else that it came from Alice. So a good example of this is where Alice is purchasing something from you, and she says, I want to buy 1 million widgets. And so now you're off building all these widgets, and then she says later on, oh, I found it cheaper somewhere else. So she'll say, nope, I never sent that message. And the merchant wants to be able to prove to somebody, no, she really did send it. So with non-repudiation, once you send it, you can't claim that you didn't send it. Anonymity is the ability to send a message. Like if you're working undercover as a policeman or something, you want to be able to send things without anyone being able to figure out who it was that sent it. Virus scanning is something where often you want a box between Alice, the sender, and Bob, the recipient, to be able to look through the message. And if it's encrypted, this might make it hard. And anti-spam is, kind of an interesting one. If we didn't have spam filters, the entire internet would just collapse. All the mail servers would just collapse from the total bulk of email. Electronic commerce, when you're buying something, everybody agrees, oh yes, you want to be able to pay for something in such a way that someone who's eavesdropping can't see your credit card number. But that's like the least of your problem. If that was so much of an issue, you'd never use your credit card like in a restaurant where there's so many people who get to see your credit card. It's not, the stealing of credit cards one at a time that's the problem. It's some database that some, big merchant that gets broken into where somebody gets hundreds of thousands all at once. But you might want to actually be able to pay for things without the merchant being able to see your credit card number. So for instance, let's say you want to buy some kitty corn, which is illegal, and you're buying it from a criminal and you're willing to pay the money to get it, but you don't want them to see your credit card. So there were some, clever protocols in which you could buy something, but the merchant would not be able to see who you were, and but the bank would be able to authorize the payment, but they somehow didn't really touch on. A routing protocol. Usually you need to handshake with a neighbor saying, hi, I'm your router neighbor, we have a link, I'm still here. How do you know if the message is from a valid router rather than somebody that just plugs their PC into the internet and says, oh sure, I'm one of these routers. And even if it's a valid router, if somebody records what a valid router says, can you then replay that message exactly and look as though you're a valid router? So how do we know that a message is actually new rather than something that a valid guy sent a year ago? And then for routing messages, even a valid router might lie. So a routing algorithm is a distributed algorithm in which every switch is doing their own piece, and you're all depending on everybody else being honest, because you don't see the whole world. What happens if somebody manages to sabotage or compromise a router and put malicious code on there? So what happens if there's actually a malicious participant in this distributed algorithm? Which happens to be what my thesis was about, was how to make a network work even if some of the routers are malicious. So DOS, in the early days of networking, the denial of service threat was underestimated. When it was a single attacker, they were limited by the amount of bandwidth that they had. So, how much trouble can you get into when you can send as many messages as you want to a single server, but you're only one guy, until people, and so therefore people worried about a single attacker sending lots of nuisance messages. But then, and then they sort of came up with all of these defenses that really are completely outdated today. So one of them is they call cookies, which has nothing to do with web cookies, unfortunately. It's just confusing when terms get. So what this was protocols like, for instance, ICE. The server, when you try to talk to the server says, well, I don't want to waste any state on you, and I don't want to do significant computation unless you can prove to me that you come from the IP address that you claim to be coming from. So it's very easy to send a message with any arbitrary IP source address, but it's a little bit harder to actually be able to receive things at that IP address. So in various kinds of protocols in the IETF, there's this thing that when you first start up, the other side sends you some random bit, and unless you can return those same bits, it won't bother creating state for you. But in these days, when you do this distributed denial of service, which is on the next slide, that's really not going to help, because these are legitimate machines that have been compromised that are sending the nuisance data with innocent owners. So knowing which of the 10,000 machines that have all been compromised, it doesn't really help you in terms of security. IP traceback was another one where they were saying, suppose there's a stream of malicious packets from one guy, can we somehow trace back where they're coming from? Which I was always a little dubious about whether that would be practical anyway, but it doesn't help, again, if the attack is coming from 10,000 compromised machines. So yeah, distributed denial of service was a chillingly clever attack where you break into lots of machines and then you command them all to attack somebody. And why would anyone do this? It turns out there's this whole underground economy where you can actually make money from it. So you can advertise and say, I have 10,000 of these zombie machines, and you can rent my zombie army for this number of machines times a certain amount of time. There will be a certain price, and so if you want to attack a particular site just because you don't like them or whatever, this is how much it would cost to rent my zombie army. Or you could attack some company and say, oh, we're security experts, we can figure out how to make it stop. And so you sort of hold their site for ransom. So yeah, cryptographic credentials where the machines prove who they are. Again, all of these don't help because they're all legitimate machines that some innocent owner, it's been compromised because they were using software that had bugs in it. So, yes? Are what the same as what? Oh, yeah, nonces are, it's a form of nonce, actually. Yeah, I mean, how people use the word. Oh, right. So the question is, what's the difference between nonces and cookies? So, right. So nonces, they kind of serve the same purpose in terms of freshness, that you know that when somebody is talking to you, it's not a replay. The cookies were more for a different purpose, which is to check to see whether you're lying about your IP address. And then there's this really cool thing called the stateless cookie that if I just want to make sure that you can receive at that, and I send you a random number, I have to remember what number I sent you. But if instead I just know a single secret and I hash it with your IP address, then I can forget I had anything to do with you, and when you send me back the cookie, I can verify that is the cookie I would have sent you. Yeah. Okay, so now I'll talk a bit about cryptography. So it's not as scary as people make it out to be. And you actually don't need to understand the math of how it works in order to understand how to use it. So it's important to understand the properties. It's not so important to be able to invent new algorithms. We have plenty of cryptographers in the world. Let them do it. Let them bless the protocols and just use them. But it's very important for everybody to understand what a public key is versus a secret key and why you would care. And I'll be talking about that. So the main features of cryptography are for encrypting messages so that you can transmit it and people can see what you transmit, but won't be able to figure out what the actual data that you sent. Integrity protection is this other thing, which is really important, where it's like a checksum, so it shows that the message hasn't been mangled, but unlike the ordinary checksum that we're used to, CRCs, this one you can't generate a correct checksum. You can't modify the message in any way unless you know the proper cryptographic key. And authentication is sort of a way of proving who you are rather than just sending a password across. So there's three types of cryptographic algorithms, three basic types that you need to understand. So secret key, public key, and cryptographic hashes. And I'll explain what these things are. And they're used for authentication and all that. So in secret key cryptography, and these people use the terms differently. But this is the terms that we tried to kind of enforce when we wrote our book. So with secret key cryptography, there's two operations, encrypt and decrypt. They're called encrypt and decrypt, but they're just inverse operations. Just like multiplication and division are inverse operations. So it's some sort of way of scrambling the message. You combine the message with the key and run it through the encrypt box, and you'll get ciphertext. And then you can reverse it by using the ciphertext and the key and using the inverse operation, which is called decrypt. So there's one parameter that both the sender and the receiver know the same number, and that's called the key. Even the person who designed the algorithm can't break it without knowing the key. So it's sort of like you might understand how a safe is constructed, and if you were an honest safe designer, so there's no hidden back door, once you sell the safe to somebody, if you don't know the combination, you can't get into the safe. So again, a good cryptographic algorithm is one where with the key, without the key, you really can't break the algorithm. And ideally, there should be a different key between each pair of users, because the more people that know the same secret, the harder it is to sort of keep it secret and to know who it is you're actually talking to. If you know that there's 100 people you talk to that all know the same key, you have to trust them not to impersonate each other. Here's my attempt at a prettier picture. I'm not a big fancy PowerPoint type. So you have the encrypt box takes your message, which is known as plain text, and the key, and combines them and comes out with the ciphertext. And to reverse it, you take the ciphertext and the key, the same key, and you run it through the inverse operation called decrypt, and you get the plain text back. For an integrity check, you take the message and the key and run it through a function that computes this integrity check, and you get an actual integrity check, which will be a 128-bit number or something. And then in order to verify it, you take your message and the key and your integrity check, and you run it through a function that takes those three inputs and then gives you a yes or no, whether the message was valid or not. So this is just sort of a cute observation. The faster computers get, do you think that that would make the good guys who know the key have an advantage? The bad guys have an advantage because they have to search through all the keys? Or does it really not make any difference because both the good guys and the bad guys get faster computers? So what's really kind of astonishing is that the faster computers get, the bigger a gap you can make between the good guys and the bad guys, where the good guys are the ones that know the key. And the reason for this is that a good cryptographic algorithm should be, the overhead of it should be linear in the length of the key. So if you have a 100-bit key and you make it 101 bits, it should only be 1% slower to do encrypt and decrypt. Whereas, again, if it's a good cryptographic algorithm, without the key, the best way of breaking it should be running through all the possible keys. So if you go from a 100-bit key to a 101-bit key, the good guys have 1% more work to do, but the bad guys have twice as much work to do because one extra bit means twice as many keys. So, to sort of say it in a different way, if performance were adequate with a 100-bit key for doing encrypt and decrypt, knowing the key. If you got a computer twice as fast, you could now use a 200-bit key and have the same performance. But the bad guys don't have twice as much work. They have 2 to the 100 times as much work when you go to from a 100 to a 200-bit key. So, that's just amazing that the faster computers get, the more powerful a tool cryptography gets to be. So now, in terms of secret key cryptography, there's two kinds of cryptographic encryption functions. One is known as a block cipher, where you chop your message up into fixed-size blocks, like, for instance, 128 bits, and you encrypt each block with the key. Sort of separately encrypt each block. And the block size doesn't need to be the same as the key size. You could use a 256-bit key with a 128-bit block. So the alternative kind of thing is known as a stream cipher, where the key is used at both the source and the destination into some sort of thing that generates a long string of pseudo-random bits. And the way you actually, and since both of them start with the same key, both Alice and Bob will generate the same pseudo-random stream of bits, identical streams. And then how you do encryption is you do an exclusive OR of the message with the bit stream. An exclusive OR is like very, very fast. And also you can generate the stream in advance before you see the message. So it's sort of it has nice properties. When you exclusive OR with the same thing twice, you get the same thing. So if you take X, you exclusive OR with a masked N, and then exclusive OR with N again, you'll get back to the original message X. So yeah, a block cipher, you take the plain text and a key as you get the ciphertext. Okay, yes, all right. And a stream cipher is you take the key, you generate a pseudo-random stream of bits that, I call the pseudo-random stream X, and then you get the ciphertext by exclusive ORing the message with the portion of the bit stream X, and you decrypt by exclusive ORing with the same bit as you use to encrypt it. Now, public key crypto is kind of a bizarre notion, but it's the coolest thing. Instead of having a secret key that you have to somehow pass between every pair of users that you want to cross, instead each user has a pair of keys, a public key that it tells the world, and a private key that it keeps secret. So the public and private key are inverses of each other. So the way to think about public key crypto is as if nobody ever invented division. They only know how to do multiplication. And you come up with a pair of numbers that are inverses of each other, like 5 and 1/5. And you tell everybody 5, and you say, if you want to encrypt the message that only I can read, multiply it by my public key, which is 5. And only I know the private key, which is 1/5, so I can undo the public key operation by multiplying by the inverse number 1/5. So obviously multiplication is not a good public key algorithm, but they come up with math such that that it's safe to tell everybody one number and they can't figure out the other one. So that's kind of a mind-boggling thing. How can it be safe for me to tell you the public key and you wouldn't be able to figure out the inverse number? And so I just say, oh, well, don't worry. The mathematicians have some way that I tell you the public key. It's impossible for you to come up with the private key. And then you're happy for like 10 seconds until you say, wait a minute, if it's impossible to come up with the inverse number, how did you come up with the two numbers to be inverses, to be your public-private key pair? And that's just a magical thing. If I had a little bit more time, it takes me only about 15 minutes to explain RSA, but this is only, which is kind of the easiest to understand public key algorithm. But unfortunately, we don't have that much time. But if you catch me in the hall sometime and really want to understand that, I'll tell you. So when you want to encrypt something, you take the plain text, you encrypt it with the public key, and you get the ciphertext. But to undo it, you use the private key. So, once it's scrambled, unless you know the inverse number, because there's no inverse operation, you need to know the inverse number. And only I know my private key, but everybody else can know my public key. So digital signatures is what, at least we tried it. In our book, we tried to enforce this terminology, which the rest of the world doesn't necessarily follow. But an integrity check using public key, we call the digital signature, whereas if it's a secret key-based thing, we call it just an integrity check. But a digital signature is one of the things that makes public key stuff so incredibly powerful. Because I can generate a message that in order to generate the integrity check, I use my private key. But anybody that knows the public key can verify that it's the right signature. Whereas with secret key integrity check, the same secret is used to generate the integrity check as to verify it, which means that with secret key, anybody that can verify that the integrity check is correct could have created the message themselves. But with public key, because you need the private key in order to generate the integrity check, but you can verify it with the public key, then you know that it had to be someone that knew the private key that generated it, even though everybody else can verify that the number is correct. Yeah, with public key integrity protection, with the plain text and the private key, you generate the signature, and to verify the signature, you need the plain text and the signature and the public key in order to verify that this is correct or not. So, yeah, repeating for emphasis, because I think it's really important. The really important difference between doing something, an integrity check based on public key versus secret key, is that with secret key, you have to trust the verifiers not to forge your messages, because they know the same secret and they could generate a message and claim it's you, whereas with public key, they can't do that. Now, cryptographic hashes is like a weird thing that you wouldn't really think you'd need. The way it came about was that when the people invented this public key algorithm known as RSA, people said, oh, yes, that's a very cute mathematical thing, but it's, who cares? It's not practical because it's so slow that you couldn't possibly sign a message, like a very large message. Let's say that you wanted to digitally sign War and Peace. You said, oh, I made this message, a huge message. You couldn't do it with RSA. It just wouldn't, it would just be too impractical to both, generate it and verify it. So what they did was they came up with this concept of taking a message and having some very, very fast operation that sort of mushes it down to 128 bits. And that's a hash. So, but it has to have very special properties. It has to be the case that you can't find two messages that hash to the same value. Oh, and the reason for that is when you sign your big message, you don't actually sign the message, you sign the hash in the message. So when you have a message, you do the cryptographic hash, which is very fast, to get it down to a small value, like 128 bits or 256 bits, and you sign the hash. So when you're signing something, you're actually signing all messages that have the same hash. Because you're not signing the message itself, you're signing the hash. So therefore, it's very important that you can't find two messages with the same hash. But if you think about it, how many messages are there of arbitrary size? Well, gazillions. How many values of 128-bit hash are there? 2 to the 128. So how many messages have the same hash? Well, zillions. But the idea is that 128, it would be like, it's such a large space that being able to, by accident, find two messages that happen to have the same value, it's a large enough space, you'll never do it by accident. And the cryptographic hashes, if it's a good cryptographic hash, you won't actually be able to somehow manipulate two messages to have the same hash. So as it turns out, a lot of the hash algorithms that have been around have been broken in terms of people have been able to do that, in which case we kind of won't use them anymore. Yes?
I really is. On this point, are there other properties that are nice to have in a cryptographic hash? So, for example, Hamming distance. If the Hamming distance between the two messages is small, I would assume that you want to store a very large Hamming distance between the hash.
Well, if it were really the case that still it wouldn't be so bad if the Hamming distance was small, but if you had something with the Hamming distance being small, the probability that it was secure that you would be very small. So in fact, a good cryptographic hash, if you change one bit in the message, it will look like a totally independent 128-bit number. And example of secret key algorithms. There was this old standard known as IETF, which had too small of a key and it was too slow. And just a 56-bit key just is too small. You can search through all of them. Triple Dead fixed the key size by basically doing DES 3 times, that if it was slow before, doing it 3 times is going to be slower, 3 times as slow. RC4 is an interesting one. It has a variable length key. It's a stream cipher. And then AES was the replacement for DES, which, it was a really interesting story that NIST is sort of a branch of the U.S. government that does standards, and they felt, they're really good guys, and they my son, by the way, works there, full disclosure, but they were saying, gee, the world needs a better cryptographic algorithm for encryption. We could just sort of wait around for it to happen. Well, that wasn't happening. So they could have gone to their buddies at the NSA and said, give us the world's best, fastest, most secure encryption algorithm, and I'm sure they could have come up with one. But after kind of years of all this export controls and doing, the industry didn't really trust the U.S. government not to try to give them something that had a secret trust line set. So NIST had at least as interesting a public relations problem as they had a technical problem, which was how could they make this thing appear and have people trust it. So they were very clever. They came up with an international competition where anyone could submit things, and there were various rules, like you had to, it had to be freely licensable, and you had to divulge everything about how you came up with these algorithms so that people wouldn't think that there was some sort of secret, nefarious way of breaking it. And so they had stuff all over the world, and the winning competitor was these 2 guys from Belgium that came up with an incredibly elegant algorithm. And so that thing was the one that was chosen for AES, Advanced Encryption Standard. Example public key algorithms, RSA has sort of an interesting feature that you can make it very fast for the public key operation, but the private key operation will be slow. So why is that good? Since you have to do both public key and private key operations. The reason why that's a very nice property is that when you sign a document, you use the private key. But you sign it once, and then zillions of people have to be able to verify it. So the fact that the public key operation is fast means that it's easier to verify it. Now, elliptic curve crypto is more efficient. It has smaller keys, so it's faster than RSA. But there was a long time, this was sort of, adoption of it was slowed by kind of murky patent situation. I would think that by now, enough years have passed, so but at any rate. So both of those are in use. Crypto-agile. Notice how many cryptographic algorithms there are. So there's this danger. If I were designing a protocol, I would like to say, okay, you're using this for encryption, this for your hash, and make it nice and simple. But these days, all of the protocols are what's called crypto-agile, where we start out saying, hey, what encryption algorithms are you willing to support? Oh, okay, well, of those, I would like to use this. Which hash algorithms instead? Because there's the danger at any moment that the cryptographers can say, oh, no, we don't like that one anymore. We might need to use this one. So therefore, protocols now are sort of a little bit more complicated because you have this handshake first, where you decide which thing to use, and then you sort of call a different function because your neighbor wants to use DES instead of AES or whatever. Encrypting large messages. There's this fancy word called modes and initialization vectors, and I just want to demystify that. So let's say you want to use a block cipher, which uses 128-bit block, and you have a message that's bigger than 128 bits. So the most intuitive thing is you chop it up into 128-bit blocks, and you encrypt each block with the key, and you send that. That's actually called electronic codebook. But the problem is if you look at the ciphertext and you see two different blocks that have the same ciphertext, you know that those two blocks have the same plaintext. So it can leak information. So therefore, people tend to not use that. Instead, they use these things that chain and take the output of previous blocks in order to decide what the ciphertext block is going to be. So an example of one is known as cipher block chaining, or CBC mode. So if we look here, what it is you take your message, ignore the ID for the moment, you break it into 128-bit blocks. The first 128 bits I'm calling M1, the second 128 bits I call M2, and so forth. You just chop up the message. And then now let's look at how you encrypt M3. Where's my little arrow? Okay, so M3, you exclusive OR it with the previous ciphertext block. And then you encrypt it with the key in order to get the third ciphertext block. So now you would think, oh gee, if you lost one ciphertext block, you wouldn't be able to decrypt anything after that. But no, it would, if you lost the ciphertext block, you wouldn't be able to come up with the plaintext block or the next one because it feeds into there. But after that, message block 4 only depends, ciphertext block 4 only depends on message block 4 and ciphertext block 3. So now every one of these message blocks has a chance to kind of randomize it by taking the output of the previous ciphertext block, except for the first message block. And so if you were to encrypt two messages that started with the same block, the same plaintext block, you would be able to tell that the first plaintext block was the same. So in order to avoid that, they come up with this extra block they call the initialization vector, which ideally is different for each message that you encrypt. And that becomes sort of the minus first ciphertext block. So in order to create the first message block, ciphertext block, you exclusive OR the first message block with the initialization vector. And this is how you decrypt. Now, when you encrypt something with a public key, the public key operations are much slower. So you would never want to encrypt a big message with a public key. So what they mean when they say you encrypt something with a public key, because they say that all the time, what they really mean is that you don't actually do what's in the top there. Instead, you take a random number and use it as a secret key, and you encrypt the message with that secret key, K. So the thing on the right over there, you take the message and encrypt it with K, but the recipient doesn't know what K is because you just picked it when you. So you have to tell the recipient what K is by also sending K encrypted with the recipient's public key. So it still has something encrypted with a public key, but the key is nice and small. So you can send a large message by encrypting the large message with the faster secret key. And you just have to unwrap the secret key, and then you can decrypt the message. Digital signatures, as I said, instead of trying to sign a message with somebody's public key, you instead do a hash of the message, and you sign the hash. You don't actually sign the message. So, and if you sign and encrypt, you do both. Oh, by the way, on this thing, how do you actually verify this? What you would do is you reverse the signature, Bob's private key, by doing the public key, and then you get the digest of the message, which is just some random-looking 256-bit quantity. In order to verify this with Bob's signature, you have to also do the same cryptographic, oh, by the way, I'm using digest and cryptographic hash as synonyms, so sorry for that. You take the message, do the cryptographic hash of it, and see if that's the same value as you get when you take the signed thing and reverse it with the public key. And you can combine the two operations. So there's no reason other than the mysterious cryptographic field for you to be inventing new cryptographic algorithms. Even if you could invent one that was better in some way, it was more secure or faster or something, nobody would believe it. So it's just, there's no percentage in it, just use the ones that have been blessed by organizations like NIST. Okay, now authentication. How do you prove who you are? Well, assuming that Alice and Bob both know the same secret key, K, instead of Alice saying, I'm Alice, the secret is K, instead you say, I'm Alice, Bob tells you to do something mathematically with K to prove that you know it. So a typical thing, he'll pick a random number, encrypt the random number using K to get some challenge C, and say, oh yeah, if you're Alice, decrypt C, and if she can come back with the same random number R, then you know you're talking to somebody that knows the same secret. Now, how did you do authentication in the olden days? And now, when I say the olden days, I mean like today, unfortunately, and probably for the next 10 years. There's password-based, where you just say what your password is. And a real severe problem with that is that how do you know you're talking to the right server? If you're talking to the wrong thing and you send your password, the thing you just said your password to can impersonate you someplace else. The passwords are really not very good. Plus eavesdroppers can do it as well. There's also a bunch of things based on addresses, looking at the IP address and assuming, oh, that must be who you are. Okay, so authenticating people. Somebody broke it down into sort of 3 categories of how you authenticate somebody. It's what you know, which are like a password, what you have, like your front door key, smart cards and stuff, or what you are, which is some sort of biometric that it looks at your fingerprints or scans your iris. Passwords are hard to get right. People can't remember passwords with enough cryptographic strength. People reuse passwords, so it's dangerous to have servers that store passwords, because if someone breaks into one server and sees what you were using as a password, then you might use the same password someplace else, or some obvious, so you might use the password 1234, but for Amazon, you might say Amazon 1234, and for CNN, you might say CNN 1234. This is what a lot of people do, because there's no way you can remember a totally independent password at every site that you go to. Oh yeah, and so the book I'm talking about, I co-wrote a book on network security, and it's called Network Security, it's sort of just to show that it can be a serious book, but still funny. This is a quote from that book. Humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and may pollute the environment. It's astonishing that these devices continue to be manufactured and deployed, that they are sufficiently pervasive that we must design our protocols around their limitations. One thing that drives me crazy is when people say we need more user training. It's like, no, you need to design your stuff to work with the installed base, which is human beings. Yeah, so passwords in the clear are considered harmful, and the IETF tries to, not approve any kind of protocols that are based on that. Now, there's another sort of notion of password guessing. So there's online attacks and offline attacks. An online attack is where, in order to guess the password, you have to actually be talking to something that can know how many times you guess. So, for instance, ATM cards that are like real money typically only have a 4-digit PIN, so there's only 10,000 possible things. It's amazing that this is considered secure enough, but it only gives you 3 guesses and then it swallows your card. Though actually I believe you can do 2 guesses and then say, oh, forget it, and you could probably keep going around to different ATM machines. But at any rate. Oh, really? Even if you go to a different machine? Oh, that's good to know, actually. Right. But yeah, so because it's an online attack and they can monitor how many false attempts you have, it's actually reasonably secure, even with a small with a small space. The alternative is an offline attack, where somehow you can get information so that you can take it back to all your Cray computers in your basement and search through all lots and lots of passwords. Now, when would a system allow you to do that? Often people use passwords and turn them into secret keys, and they use them instead of just sending the password. They convert the password into a secret key. So, for instance, this is a typical kind of protocol where Alice types her password into her workstation, and the workstation computes some sort of hash of the password so that it has the right form factor to be a secret key. It's now 128 bits or whatever. And the server knows the hash of the password. So now the workstation says, I'm Alice, because Alice says, my name is Alice, and here's my password. And the server sends challenge, and the workstation computes, takes the challenge and encrypts it with the hash of the password. Now, the problem with this is that somebody who eavesdrops on this can steal R and the encrypted version of R that's encrypted with the password. And now, in his basement, he can go through every possible, through millions of passwords quite efficiently without being monitored to see if, if the password were this, is this how R would be encrypted? Now, there's other ways of authenticating people. There's this IETF protocol called OTP, which stands for one-time password. This is actually elegant enough that even though it's kind of not terribly relevant, I just sort of felt like describing it, so I threw in a slide. And various tokens which kind of look like little calculators that can be based on challenge response. We get a challenge, we type it in, and a number appears, and you have to type it in. And then in IETF, there's Basel and EAP, which are frameworks for negotiating what kind of authentication to do. So a token card, these things that look like little calculators, they should be 2-factor. Somehow it should, and if someone steals your token card, you don't want them to be able to impersonate you. So there should be a way of putting in a PIN as well. Time-based is sort of cool. Every minute, your token card is displaying a function of your secret, which is in the card, and you don't even know it, and the time of day. And so then there's interesting problems with clock skew, because the clock at the server might be going faster, and then sequence-based, which is every time you press it, it encrypts the next sequence with the secret. So this is the Lamport cache, which is also known as ST, which was an implementation of it, and OTC, which is the name of the RFC. So, well, you know what, I'm worried about time. So it's an incredibly cool thing. Okay, so now I'm going to talk about trusted third parties. It's sort of for how you do key distribution. How do two people get into groups? How do you find out? How do you get a secret key configured for every pair of SIN? So, you know, I guess you were trying to do secret key on the internet, and you had to configure a separate key between your machine and every other machine on the internet. This would be pretty horrible. So people wouldn't do it that way. Instead, they have a magic box that's known as a key distribution center, and that box knows a secret for each user. And each user only needs to know a single secret, which is the secret they share with the KDC. So this is basically how the protocol Kerberos is. So there's this magic box, the KDC, that knows a secret for each user. So this wouldn't scale to the whole internet, but it scales to some sort of size of domain or whatever, maybe a whole company. So the KDC knows every user's secret. Each user only knows its own secret, which enables everyone to talk to the KDC, but who cares? You don't want to talk to the KDC. Alice wants to talk to Bob. So if Alice wants to talk to Bob, she has to ask the KDC to introduce him. So Alice sends a message to the KDC saying Alice wants to talk to Bob. The KDC invents a secret for Alice and Bob to share, and can securely send a message to Alice encrypted with Alice's secret, saying, if you want to talk to Bob, use this secret that I just invented, which is K sub AD for Alice and Bob to share, and can send a message to Bob securely saying, if you want to talk to Alice, use the secret K sub AD. And now Alice and Bob share a secret. And yeah, for those that know Kerberos, just so you don't get upset, the KDC doesn't actually bother talking to Bob. Why should it have to look it up in DNS, and what happens if Bob is down right now? What the KDC does is take the message it would have sent to Bob and send that to Alice. So, because Alice is the one that's asking. And this is that bunch of bits it would have sent to Bob is known as the ticket to Bob. So it says to Alice, if you want to talk to Bob, use K sub AD, and here's a pile of bits that you can't decrypt, but give it to Bob, and he'll know what to do with it. So when Alice wants to talk to Bob, she sends the ticket to Bob, which he decrypts using his secret, and inside is a message saying, someone named Alice will want to talk to you, and will know the key K sub AD. So that's basically how Kerberos works. Now, with public keys, when I first in the 1980s saw public key cryptography, it was like, oh, wow, we solved the key distribution problem. Because it's easy. You just announce to everybody what your public key is. You don't have to keep a secret. But the problem is, unless you know for sure that a particular public key goes with a particular name, you don't really have any security at all. So you still have an important security problem, which is knowing which public key goes with which thing. Because if you get a signed message, you have to know, and it says it's from Alice, you have to know that was Alice's public key. You can't just have somebody say, oh, I'm Alice, this is my public key. So in order to do this, in order to make it secure that you really know that the right public key goes with the right name, is that there's this thing known as a CA, or Certification Authority, that signs a message known as a certificate that says, I vouch for the fact that the name Alice goes with this public key. And once it's signed, you can put it, you can just post it in a public place because, that doesn't have to be secure because the certificate doesn't have to be secure and nobody can modify it. So if you look at how Alice and Bob talk to each other with public keys, Alice just sends her certificate to Bob saying, my name is Alice, this is my public key, and it's signed by the CA, and Bob sends his certificate. And now once each side knows the other side's public key and knows their own private key and knows the CA's public key so they can verify the certificate, they can both talk securely. So now let's compare the functionality of the secret key approach with the public key approach. The secret key approach with the KDC is less secure because you have this online box with a highly sensitive database. It knows everybody's secrets. So if you were to steal that database, you now know everybody's secrets and you can impersonate them. The KDC has to be online and accessible all the time because in order for anyone to talk to anyone else, you have to be able to talk to the KDC first. And because it's online, it's an attractive target. If it has any bugs whatsoever, someone might be able to break in. Whereas the CA doesn't have to be online. You can create the certificates offline and post them, and there's sort of no meaning to a bug in the CA because no one can access it in a vault except for once a week when you have your new employee orientation, you go down and you drag out the CA and generate certificates for them. Also, the KDC has to be replicated. Because if it goes down, you better have more than one copy of it. In which case, any one of them, if somebody can get physical access to it, you can, compromise it in various ways. The KDC solution is going to be more expensive because you need multiple boxes, and the box is performance sensitive. Whereas the CA is just a glorified calculator. If it took you a minute and a half to create a certificate, who cares? Now, performance, the actual public key crypto is slower, but that's dwarfed by the fact that you have to talk to an extra box before Alice and Bob can talk to each other. The public key stuff works better through firewall because if you have a company, it's unlikely the firewall administrator will be willing for people from the outside to be able to talk to your most security-sensitive box, which is the KDC. Whereas with public key, you can just email your certificate to the other side. Revocation, which I'll talk about, does level the playing field a little bit because if you want to revoke somebody's certificate, you do need some sort of online box, but it is not as security-sensitive as either a CA or a KDC. So revocation. What happens if somebody steals your credit card? Well, it has an expiration date on it, so maybe we don't have to worry about that. But the expiration date is like a year from now. So if somebody could misuse your credit card for a whole year, this would be unpleasant. So, well, you could maybe make the credit card expiration date be 1 day, but then you'd be getting a new credit card in the mail every single day. This would be annoying. So you don't want to depend on the expiration date to do revocation. You want something that will allow you to have a certificate that lasts for a really long time, but yet revocation can happen quickly. So in the old days of credit cards, the credit card companies published a book of bad credit card numbers that they would publish and send to all the merchants. And when you tried to buy something, they'd have to look through the book. And this was very expensive, and they couldn't send it out more often than once every few days. So instead, they've gone to an online model where there's some central database that when you try to buy something, it talks to the central database and says, has this, is this a bad credit card number before the merchant accepts it. So the digital equivalent in the public key world, there's something known as a CRL, which is a certificate revocation list, which is like the published book of bad credit card numbers. And then there's also the online model, which there's a protocol for talking to the online thing, which is in IETF, and it's called OCSP for Online Certificate Status Protocol, where you can go and ask it if this thing's valid. So another philosophy, like KDCs and CAs, is known as identity providers. And usually the cryptographic stuff is based on the standard called SAML, which is done not in IETF but in W3C. And it uses XML syntax, which I just can't get excited about what syntax anything is. And the idea is that the user authenticates to an identity provider, and then the identity provider gives you a message that is signed saying, yeah, I checked this person out, and it's Alice. Now, that I don't consider as secure because it's something that now it's like a password in a sense, that once you give that to somebody, even though it's cryptographically signed and all that, if you give it to the wrong guy, he can impersonate you with somebody else. Because, okay. Yeah, the SAML is just an encoding. It could be used just like a certificate. And then you'd have the extra step that even though you send somebody your certificate, you still have to prove you know the private key. But it doesn't tend to be used that way. It tends to be more used as a bearer token, which means that just knowing this pile of bits means that it's you, which means that there's sort of, it's a little bit less secure. Okay. So now another interesting issue is, people tend to get sort of all enthralled with the syntax of things and argue interminably over which fields should go there and stuff. But there's, kind of bigger issues other than the syntax of a certificate. So here's, one to think about, which is that you're not going to have one KDC for the entire world. So you're going to need to somehow have chains of trust. And I'll talk about the various ways of doing that and how I wish things were, but in general, people are not doing it that way. So the strategies for these trust hierarchies, I just give them cute names of monopoly, oligarchy, and you'll see what I mean. So the monopoly model is where you choose one organization universally trusted by all companies in all countries. You embed their public key in everything, and everybody has to get certificates from them. This is nice and simple to implement, but what's wrong with them, with this model? Well, monopoly pricing. You shouldn't ever design something where you give one organization such power, because if they're clever, they'll first give it away like crack until the world is hooked on it, and then gradually raise their prices, because the more widely deployed it is, the more hard it is to move away and start over. So if they only raise their prices kind of slowly enough, then they can eventually get all of the money in the world or something. Getting a certificate from a remote organization is going to be insecure or expensive or both. How would some organization, let's say Verisign, know that I'm Radia Perlman at Intel? So that is a problem. Also, that key can never be changed. It's just a good idea to change keys occasionally in case, well, for one thing, maybe the cryptographers will decide that they think that the keys should be longer or that you should switch to a different algorithm. And the security of the world depends on that one organization never making a mistake. And certainly there are great examples where well-known organizations have made really embarrassing mistakes. So another sort of way of modifying this model is that you have one CA, that's the one that actually grants the certificate. But instead of having this one organization, let's call them CA plus just so I'm not using any organization's name. So CA Plus is the one organization that creates certificates, and everybody knows their public key. But instead of CA Plus having to check me out to make sure that I'm really radiopharma at Intel, Intel would have its own thing that's called an RA, or a registration authority, and it's the thing that checks me out, and it sends a message to CA Plus saying, I checked her out, you know me, I have a relationship with this, please issue a certificate with the name Radia with this key. So, that does make it easier to check people out, but it still is the same monopoly model. Okay, oligarchy. So this is kind of how the browsers work. They come shipped with some number of trusted public keys. One thing that annoys me is people call things self-signed certificate. What is a self-signed certificate? It says, I vouch for the fact that I am Radia, this is my public key, and I'm signing it with the key that I'm just telling you. So there's no security there whatsoever. It's just a convenient format because the implementations knew how to parse a certificate. So to bootstrap, rather than just sending a raw public key, you send it in as if it's a certificate, but it's not a certificate in any sense. It's exactly the same as just storing the public key there. But at any rate, so your browser comes with a bunch of public keys that your browser trusts, and any certificate presented to the browser with any of those assigned with any of those keys, your browser will be happy with. Usually, you can add or delete from the set. It does eliminate monopoly pricing, but there's this mind-boggling number of these things. How could you actually check to see if somebody actually put extra public keys in there? And even, in this thing, it says, let's say that you trust GTE Cyber Trust. The fact that it's here with that name doesn't mean that it was really that organization. Somebody could have removed the real GTE Cyber Trust and put in a false self-signed certificate with a different key. But at any rate, this model is less secure because before it depended on being able to find an employee you could confuse or bribe or threaten at one organization. Now you have 80 organizations to find some employee at, so it will be less secure. So the next sort of wrinkle in these things is to have a chain of certificates. So your browser may only know a certificate, and it may only know a public key. But somebody could send you a chain of certificates saying, A says this is B's key, and you should trust B. B says this is B's key, and you should trust C. And C says this is Radia's key. So with this chain, it's you don't need to have A, B, and C's key already in your browser. So now, with that model, there's this model that I call anarchy, which is how PGP was originally deployed, which nobody tells you who to trust. You just, you've met people and you think that they're trustworthy and they give you their public key on a business card, so you configure your own machine with who you decide to trust. And then every time you have a gathering of nerds, like an IETF meeting, you have a PGP key signing party with some sort of elaborate ritual where you say who you are and what your key is. I bet they're having a PGP key signing party here, but at any rate. And so then there are public repositories of PGP certificates. Anybody can sign one, and anyone can donate it to these databases. And then if I want to talk to Joe Smith, and I don't have his key in there, I try to piece together a chain from one of the keys I have configured in my own machine. I try to find a path through the certificates in the public database to get to Joe Smith's key. So what's wrong with this? Well, it's not going to scale. If you want the entire internet based on this stuff where anyone can sign anybody else's certificate, it's just to look through this database. If you imagine 1 billion users and each one signs 10 certificates on average, that's just too many to look through. But worse yet, even if you find a path, how do you know whether to trust it? So, once it gets beyond the people you've really met, you have no reason to know. You've never heard of this person. So, and the way that people tend to believe they should do these things is that they have some sort of pull-down menu where the user can look at the path if the user wants. And then the user gets to say whether it's secure or not. And that's completely unreasonable. I mean, the implementer of this technology then thinks it's the user's problem. It's the user who said the path was okay. But it's just completely unreasonable for the user to have to look through a chain and say whether it's, whether everything in the chain is trustworthy. Okay, so the next wrinkle is top-down, where everybody kind of starts with the public key of the root, and then you have a namespace, and you know exactly what path to follow because it follows the namespace. So, for instance, with the DNS namespace, you have a root, and then the root would sign a certificate for .com, and .com would sign a certificate for Intel.com, and so forth. But the problem is you still have the monopoly problem, that you still have one key that everybody has to be configured with, which is the root key. So the model that I prefer, I call bottom up, which is that you have a hierarchical namespace, just like DNS, but instead of just having the parent node in the namespace sign a certificate for the key of the child, you also have the child sign a certificate for the key of the parent. And that way you don't have to start at the root. You can start any place and navigate through the tree to where you want to go. And I'll explain why that's better. So let's say that you're Alice and you want to get Bob's key. You only have to, and let's say that the key you start out with is your own key. You only have to go up to a common ancestor and then go back down. But if you're trying to talk to Carol over here, you have to go up 2 levels and then go down. Now, if you don't want to wait for the whole PKI public key infrastructure of the whole world to get connected, you could build a little PKI in company ABC and another one in company XYZ and have the top of each one of those cross-certify each other's keys. And then everybody here is now connected to everybody there. So a crosslink is where any node is allowed to certify the key of any other node. Now you might think we're back to the anarchy model. But no, the reason it's not is because you only follow a crosslink if it leads you into the namespace of the target. You don't follow a link to HP in case HP knows IBM's key. So you basically start wherever you start. If you're already at an ancestor of the target, you go down. Otherwise, you look to see if there's a crosslink that gets you into an ancestor of the target, and then you go down. Or you go up a level and look for a cross certificate. You go up as many levels as necessary to get to either a common ancestor or to one crosslink, and then you go down. So, and you can add roots, and still you keep going up 1 level and go down. So the advantage of this model is that to build a PKI in your own organization, you don't need to buy certificates from anybody else. You just deploy it inside. Security within your own organization is entirely in your own hands. So what's presumably kind of most security sensitive, which is authenticating users and resources in your own organization, it doesn't matter if every CA in the rest of the world gets compromised. The actual path that you'll use of certificates are only through CAs that your own organization controls. There's also no single compromised key that requires massive configuration. Now, you might think if you did have a root here, if that got compromised, you'd have a big disaster on your hands. But no, for some lowly user at the bottom here, if your organization decides they don't want to deal with that root anymore and need to change the key, they have to go through the fancy revocation and new certificates and stuff, but it doesn't affect me as a user. My key stays the same, all the certificates that I know about stay the same, and it's just by magic, next time I try to follow the chain outside of my organization, it'll be a different certificate, but, I don't care. It'll all happen automatically. Comparison. This is leading into another, slides got slightly out of order. So this was just something else I found sort of interesting. If you compare IPsec and TLS, they sound alike. They're both doing mutual authentication, establishing a shared secret, and then cryptographically protecting the conversation. So what's the difference? Well, IPsec is layer 3 and TLS is layer 4. So great, if you're taking a quiz, you know what to write down as the answer. But what does it mean that one's layer 3 and one's layer 4, and why would you care functionally? So, that's the kind of question that I always find interesting. So the IPsec idea was, let's do it totally in the kernel. Let's modify the kernel and do that work once, and then automatically all of the applications will be secured as a result. Whereas the TLS idea was, let's not modify the operating system. Let's only do it as a user-level process on top of TCP. Comparison. IPsec and now they've changed TLS. They have a version of it called DTLS, Datagram TLS, which runs instead of on TCP, it runs on top of UDP. And so then it has kind of similar functionality as I'm about to describe as IPsec. So they protect a packet at a time. Each thing you send across the internet is individually packaged up. Whereas with TLS and SSH, it's sitting on top of TCP. I redid the slide in a way that I'm now confused by, so sorry about that. This is the original slide. So IPsec, the advantage is that it doesn't have the rogue packet problem that a protocol sitting on top of TCP has. So the problem is the idea of running on top of TCP is that TCP doesn't have to be modified. It has no idea that any fancy cryptography is going on. So if you're doing TLS, there's a trivial denial of service thing, which is that somebody can create a packet that looks like a valid packet to TCP. And TCP won't know the difference because it's not participating in the crypto. Once it accepts a certain number of bytes, if a bad guy put in some random bytes in there, there's no way for TLS, even if it knew that those were bad bytes, to tell TCP, oh, wait a minute, those were bad bytes, back up. If TCP sees the right stuff, it's going to throw them away. So that's why it's sort of nice with IPsec, where each individual packet is protected. No one can inject a bad packet and confuse your connection. Whereas TLS, if you did inject a bad packet, there's no recourse other than breaking the connection and starting over. But the IPsec disadvantage is that all it's doing is the philosophy of IPsec was that you're not going to change the applications or the APIs to the application. So the problem with that is that you do all of this fancy authentication based on certificates, and so IPsec has now authenticated that I am Radia Perlman at Intel, But if you don't change the API and you don't change the application, the only thing you can pass up to the application is, I'm talking to IP address 79. So if the application actually cares who it's talking to, then you have to do some username password after you establish. TLS, the way it's used, really only assures the client that it's talking to the right thing. Even though, eventually you could put in client certificates and stuff, but yeah. So GTLS is sort of a compromise where it's doing TLS, but it's on top of UDP instead. Okay. Creating a session key. How am I doing on time? This is just so cool that if you haven't seen it, I just sort of felt I had to talk about it. Diffie-Hellman is this amazing protocol where, it's like the best magic trick ever. So it could be that I've never spoken to you before, and so I'm going to say a number to you that everybody in this room will hear. And you will say a number to me that everybody in this room will hear. And after these two messages, where I send you a number and you send me a number, you and I will know a secret that nobody in this room knows. Isn't that astonishing? So, and it's very easy to understand, I believe. So, this is based on the following math thing that we assume is hard. Now, why do we assume it's hard? Well, because mathematicians have been playing with this for a long time and they haven't figured out how to do it. So the particular math problem is that if you know a number G, which might be 7, some number, and if we haven't decided in advance, I can tell everybody, hey, we're going to use G will be 7, P will be this huge prime number, which, everybody knows what G and P are. And if you know G and P, and you know G raised to the power X, mod P, modular arithmetic is you divide by P and take the remainder. So if you know G and P and you raise G to some unknown quantity X, mod P, so you get some number that's between 0 and P, what is X? What number did I have to raise G to, mod P, in order to get G to be X mod P? And nobody knows how to do that other than plugging numbers in, saying, well, gee, if I raise G to the 15 mod P, would it be that number? Nope. And as long as P is a large enough space, nobody knows how to do that. So if we assume that that problem is hard, this is how Diffie-Hellman works. So Alice and Bob are going to agree on what G and P are, and the whole world knows what G and P are. Alice chooses a random number A, Bob chooses a random number B. Alice raises G to the power A mod P. Bob raises G to the power B mod P. Alice sends G to the A mod P to Bob. Bob sends G to the B mod P to Alice. Alice takes what she got from Bob, raises it to her secret number A, and if you remember 11th grade arithmetic, if you take G to the power B and raise it to the power A, you'll multiply the exponents. You'll get G to the power A times B. Bob takes what he got from Alice, which is G to the A, raises it to the power B, gets G to the A times B. So Alice and Bob both know G to the AB mod P, and even though everybody saw G to the A and saw G to the B, they can't glom them together somehow to get G to the AB. But Alice and Bob can, because Bob knows B and Alice knows A. So this is like the world's coolest protocol, because it's really simple to explain. But there's a problem, which is known as the man-in-the-middle problem. It was funny, in our book, the publisher tried to kind of look through to make sure there was nothing objectionable in there, and so they decided calling it man in the middle. They said, can't you come up with a word that's more gender neutral? Like person in the middle, and we said no. So, all right. But we gave the name of the person in the middle, Trudy, so it sounds female, whatever. Trudy for intruder. So let's say that Alice wants to talk to Bob across the internet, so she says, okay, Bob, I want to talk to you and I want to have a secret number so that we can encrypt everything and be secret. So she says, I want to use GBA mod P for my Diffie-Hellman number. Trudy, which is malicious software running on some router in between, removes GBA from the wire because she says, oh, I see they're doing a Diffie-Hellman. Comes up with her own number, G to the T mod P. Sends that to Bob. Bob sends back G to the B mod P. Trudy intercepts that, replaces it with her number G to the T mod P. And now you'll have Diffie-Hellman agreeing on two different secrets. One is between Alice and Trudy, which will be the secret G to the AT, and the other is between Trudy and Bob, which is G to the T times D mod P. Now, how can Alice tell whether this is going on? She could say, okay, now that we are encrypting everything, I want to make sure I'm really talking to you. What cafe did we meet at in Paris? Trudy decrypts it and re-encrypts it. So it's very hard for Alice and Bob to tell that this is really going on. So if you actually had like a encrypting telephone, the technique that this should be used, the fancy word is called channel binding, but your phone would show you a hash of your Diffie-Hellman number, and over the phone you actually say to Bob, I think that the hash of our key is such and such. Now Trudy, even though she can decrypt and re-encrypt, she can't impersonate your voice and all this fast enough to, and also the hash would be incorrect. So that's kind of a way of getting rid of the man in the middle. But if you can't do that because you don't have human beings to do that, the standard technique is known as signed Diffie-Hellman, where assume that Alice and Bob have RSA public keys. Alice signs her Diffie-Hellman number, GBA mod P, and Bob verifies Alice's signature before he uses it, and Bob signs his, and then Trudy can't be in the middle of it. So this is all nice until you say, hey, wait a minute, if they have public keys and certificates, why are we fooling with Diffie-Hellman? Why not just encrypt things with Bob's key when you send it to Bob? And the answer is this property called perfect forward secrecy, or PFS. PFS is a property such that if somebody were to record the entire conversation between Alice and Bob and then steal all of the secrets that they know, they wouldn't be able to break the conversation. So with signed Diffie-Hellman, if you forget your shared secret and you forget A and B after the conversation is over, even somebody that completely looks through everything on your machine will not be able to decrypt the conversation that they recorded. An example of a protocol that doesn't have perfect forward secrecy, and this is how SSL, at least there's a lot of variants, but this is the most common one, is that the client picks a secret key, K, and sends that to Bob, and then you protect the conversation using K. So if somebody were to steal Bob's private key later on and stole the first message, they would be able to decrypt it and get K.
I was basically wondering, is there also performance advantage to using Diffie-Hellman in addition to the has? Because we're not going to use private keys to decrypt them, shorter Diffie-Hellman shared secret.
No, I mean, Diffie-Hellman is also a slow public key thing. So you wouldn't want to be doing it all during the conversation, but it's fine to sort of set up the secret key that protects the rest of the conversation. Diffie-Hellman is certainly more heavyweight than what's on this slide here, where you just have one side pick the secret and send it to the other side and say, this is the key that I want to use. But this one doesn't have perfect forward secrecy. Now you could do it without Diffie-Hellman, and this is sort of really cool. So there's a variant of TLS, which was ironically invented because the government was trying to make it difficult to deploy good crypto, and so they were saying, oh, you're not allowed to have long enough public keys. So at any rate, because of that, they came up with this thing, which Bob has a very large public key that he uses to prove he's Bob, but it wasn't allowed to actually encrypt the key with a large public key for bizarre reasons. It didn't make any sense. But so the server's public key, Bob is the server, has a certificate with, let's say, a 4,000-bit public key. But Alice wasn't allowed to encrypt the K, the secret, that she's sending him with a 4,000-bit key. So Bob, every few hours, generates a 1,000-bit key, or whatever was legal, and signs that with his long key, saying, this is my temporary key. So he sends that to Alice, and Alice encrypts K with the temporary key. So this gives you perfect forward secrecy, because every time Bob forgets the temporary key, you have perfect forward secrecy. You can't decrypt the previous conversation. Another kind of thing that people think about, okay, I'm running low on time, is replay. Usually you use you could use a sequence number. Replay on an authentication thing, that's where the nonce comes in, where when you're proving who you are, I send you sort of a number that should be unique for the time. It might be the time of day, and you have to weave that into your cryptography so I know that that's fresh. But here, let's say that we have a TCP connection, and we're encrypting it, the entire thing. Well, TCP has a sequence number that's like 32 bits, and so it could actually wrap around. So one thing you could do is negotiate a new key before it wraps around. But another thing that's kind of clever that several protocols are doing is that you pretend that you have a bigger key than 32 bits. But you don't send the extra bits on the wire because the protocol doesn't have a way of doing that. But when you're computing the cryptographic checksum on it, you throw those extra bits in. So that's called an extended sequence number, which I thought was really cute. DNS checks. When you look things up in DNS, how do you know that you're getting secure stuff back? It would be nice if the DNS servers didn't have to be super trusted. So instead, it would be nice if you signed the things offline. And so DNSSEC provides an ability that not only when you look up and you say, what is Amazon.com's IP address, but it signs it so that you know that this really does go with this DNS name. It also provides a public key of the child then. So this is the top-down model, which I'm sort of not too happy about. It could have been the bottom-up model. And if one of the records in the DNS entry were the public key of the server, then DNSSEC could be a perfectly reasonable, lightweight PKI. And there's a working group called DANE, D-A-N-E, I forget what it stands for, which is putting in server names. Does someone know what it is? Yeah, it doesn't matter. They can look at it. Oh, DNS authentication of named entities? Okay, yeah. Okay, so now I'll just sort of talk a little bit about security considerations section. Security consideration. Every RFC needs to have the security consideration section. What do you have to think about? Now, a lot of people were always tempted to say, we're just going to run on top of IPsec. And so, the IETF is not going to let you get away with that. Sometimes, going out of your way to protect one protocol, whereas there's a million of other ways of doing a lot more damage, it really doesn't make sense to have to say, well, every new protocol has to use, heavy certificates and all that kind of stuff. If it's in some sort of environment where there's a million other things you can do, there really is no reason to worry about it so much. But sometimes you can actually argue that We haven't done anything to add to the security of this, but because there's all these other things you could do anyway. Okay. We don't need to protect the protocol. We need to protect the user. So kind of think of it more holistically. So in a security considerations section, what are the threats? And what's in scope, what aren't, and why? So, what threats are defended against? So you could say, well, it's possible that somebody could burn your data center down, and we're not addressing that threat with this protocol. So even if your protocol doesn't do everything, if you at least have thought about it and said it in the security consideration section, a lot of times that will make them happy. Sometimes there's implementation or deployment issues that affect the security. And so there's this RFC 3552 that, there's no way to give you a cookbook for how to come up with it. It's going to take some thought and advice from, people. And as I said, the best way to do that is to make your stuff not incomprehensible. Don't give someone a 600-page spec and say, help me write the security consideration section. Come up with a way of explaining your protocol conceptually, like I've tried to do today. So that, in an hour and a half, you should pretty much now feel more comfortable with the security field. So I would like to challenge people to do that in other areas. Oh, and by the way, so the EDU team, I would like to see more of these sorts of overview, conceptual introduction to fields, to areas. And so if you're interested in doing that, I'm one of the co-chairs asking about it. An example of security considerations. You can put an integrity check on routing messages that defends against someone who isn't a router from injecting routing messages, but it doesn't prevent outsiders from answering our messages and claiming that they're really somebody else and hijacking all of their traffic, or corrupting the DNS information so that once somebody has the wrong IP address for somebody, they'll be sending it off in the wrong way. And it doesn't protect against Byzantine failures where like a trusted router has been compromised. So it knows the key, all the credentials, but if someone has compromised and put on the wrong key. SNMP is a management thing. It should be straightforward end-to-end security, right? But you can't depend on, SNMP has to work even when you can't get to DNS and you can't get certificates and things like that. So that sort of makes SNMP interesting. Non-crypto things, so like DHCP, without any crypto, you could use up all of the addresses. You can just keep pretending to be different nodes and ask for IP addresses until they're all used up. So just putting crypto into DHCP is not going to help that. Interface to a human, like with certificates, a Russian S looks like a US C, and so you could get a name that looks okay to a human, and a certificate that says you have that name, but totally confused the human. Email, it's trivial to email. The message path leaks information. You can look to see what the message path was, and there's a way of asking if an email address is valid, which is both good because you can see if a spammer sent it to you, but bad because it allows spammers to find valid email addresses in order to send spam to you. And even if you do all this fancy cryptographic protection of the email, like with SMIME, I don't know why, but they decided not to protect the header. So like if I'm sending you an email with SMIME, and somebody had sent some absurd thing saying, oh, I think that on Thursdays everybody should wear bikinis or something. And send that to you, and I put in the subject line, fire this bozo immediately, that's not cryptographically protected. So somebody could take that signed message, change the subject line to brilliant idea, implement it immediately. So anyway, Kerberos. I really liked their security considerations section. It was sort of very well thought out. So it says it solves authentication. It doesn't address authorization. So Bob knows that it's Alice, but Kerberos doesn't do anything about saying what Alice is allowed to do at Bob. It doesn't do denial of service. It doesn't do perfect word secrecy. It requires an online database of keys. So the KDC has to be physically secured. It's subject to dictionary attack because the user takes their password. It's using the password as a secret key in the way that I showed the offline attack. It requires reasonably synchronized clocks because for freshness you're using clocks. Yeah. Okay. Oh, and so I'm finishing just on time. The last thing is a quote from my co-author that he said in a talk about 10 years ago that I thought it was so cool. And I always like to end on some sort of joke. Anyway. Until a few years ago, you could connect to the internet and be in contact with hundreds of millions of other nodes without giving even a thought to security. The internet in the 90s was like sex in the 60s. It was great while it lasted, but it was inherently unhealthy and was destined to end badly. I'm just really glad I didn't miss out again this time. So anyway, thank you.